Hello everyone, I'd like to talk about this new component I got, the TLC5916. This little IC at the centre of the board. It's a shift register with a couple of nice features for driving LEDs. The first nice feature is that it's constant current, so you can tell it how many milliamps to put out on each pin. So I've currently got it set up to deliver 20 milliamps, but I could adjust it to deliver a different number of milliamps. Now that's independent of the characteristics of the load, provided that you don't do something ridiculous like sticking a huge resistor on there. So different LEDs, it will provide 20 milliamps regardless of how many volts your LED wants. You don't need individual resistors for your LEDs because it's constant current. It will automatically limit the current anyway. No need to mess about with individual resistors, and it just saves on wiring and complication and confusion like that. The second advantage is that it can provide a bit more current than standard shift registers. So something like a 74HC595 will provide about a bit less than 10 milliamps per pin. This thing will very happily provide 20, which is what you want to drive an LED at nice and brightly. I can see from the data sheet it goes up to 100 milliamps and maybe beyond. So what's a shift register? There are lots of tutorials about them. Basically it's a way of taking input on a couple of wires. There's a third wire needed for control. And then independently controlling 8 different pins. So a shift register control 8 pins from 3. Another nice thing about shift registers is you can chain them together without using any more pins on your Arduino or whatever. So that you could, if you had 4 shift registers in a row, you could be controlling 32 pins from 3 pins. On your Arduino, you could control hundreds, thousands, whatever, only using 3 pins on your Arduino. They're potentially very nice like that. So for this little demo, I went for the classic Knight Rider or Cylon pattern. That only has one LED lit at a time, but to demonstrate that you can control all the pins independently, let's shift to a different mode. If I run a grey code program, that's cycling through various different possibilities. So that's showing that all 256 possible combinations of lit and unlit LEDs are possible. Using the shift register, all 8 LEDs can be controlled independently. So how quick is this thing to update? There are 2 methods to shift data into your shift register. The first way is using the shift out command, which does everything through software and it doesn't matter which pins your things are on. A second method is using SPI, which uses some special pins on the Arduino, and that's done using special hardware. So I put a few timing checks in, and if I run the timing checks, you can see that shifting out is not exactly slow, but maybe it's not blisteringly fast, whereas using SPI is crazy fast. You could do all sorts of clever persistence of vision and so forth things if you shift out your data in SPI mode, no problem at all. So one of the nice things you can do is light painting. I made a little light painting mode, which first thing it does is it turns off the backlight for the display. And secondly, there are some LEDs flickering a bit too fast to see what's going on, but if you get the board and wave it around in front of a camera set to long exposure, then you can get some interestingly patterned light trails. So last night I was playing around with it, and I'll show 1 or 2 pictures of the light painting in action. So I talked about constant current, but there's one little issue to deal with. If I turn on all of the LEDs and turn on my trusty multimeter, I've got my multimeter connected between the ground rail and the power rail, and you're seeing 4.7 volts. That's odd. It should be 5 volts. Evidently the power supply isn't supplying the full 5 volts. If I go on to just one LED at a time, then you're looking at about 4.9 volts. So having a little power supply trouble here. So if I get this 9 volt battery and a barrel jack lead and plug it in like so, you can see we're much closer to having 5 proper volts now, and 5 proper volts if I light all the LEDs at once. Now we've got 5 volts to play with, just a few things to demonstrate. These LEDs, the anode connects to 5 volts, the cathode connects to the power supply. So by doing an analogue reading, scaling it to 5 volts, and then subtracting the voltage from 5 volts, you can see what the voltage across the various LEDs are. So across these green LEDs it seems to be about 2.4 volts. Across the yellow ones, 2.14 volts. Across these red LEDs, 2.01 volts. Now, one nice thing about this chip is that you can adjust the amount of current going through, and it's controlled by a resistor that goes from one of the pins to ground. Here I've got a 1K resistor going through a 10K potentiometer. At the moment the potentiometer is adding no extra resistance, but if I dial in an extra 10K, then you can see that all the LEDs dim. You can also see that when you've dimmed these LEDs, the voltage they're drawing goes down a bit, and when you brighten them up, they draw a bit more voltage. So their voltage isn't completely stable, varies by about 100 to 300 millivolts or so, depending on what sort of current's going through them. To demonstrate that some of the voltages can really vary depending on the LED type, if I swap out this green LED and put in this violet LED that I've got handy, hold on a sec. Yeah, this violet LED is drawing 3.26 volts on full power and something like 2.87 volts on low power. It's quite a difference. So how about measuring the current that these LEDs are drawing? If I do a little diversion, if this last LED, I don't go directly to ground, but I add a little 100 ohm resistor into the loop, then gosh, that the pair between them, they're taking 4.38 volts. But you can see now with the setup, if we just move where our ADC is reading, we can see what the voltage is between the ADC and 5 volts. And you can see that it's about 2 volts. So V equals IR, we're a 100 ohm resistor, so that's indicating that we're getting about 20 milliamps going through, which is great because it's roughly what we wanted, and that's with a 1K resistor and the potentiometer set to minimum. If we drive the potentiometer to the maximum, then the voltage across the resistor goes down to about 0.19 volts, so that's indicating that we've got about 2 milliamps going through it. So that, as you can see, makes your LEDs a lot dimmer, which may or may not be what you wanted. So, to sum up, it's a nice thing. Is it worth it? There's a couple of nice features that make it more convenient to work with than a normal shift register. On the other hand, it is a bit harder to get hold of, and it's definitely more expensive than a regular shift register. So to decide whether it's worth the trade-offs, you're going to have to make a decision. Personally, I quite like the one I've got. I think I'm going to make it into like one with some RGB LEDs or something. So maybe you might get to see it on this channel. Until then, goodbye.